Hello guys. So I'm recording another video. For now I will skip a few of the previous lectures to get on top of our current material. It becomes rather difficult to film on campus. I hear sirens all the time, morning, night, the non-stop sirens. A lot of people are afraid, and as a result of that fear, they lock the campus more and more. I had to argue to be allowed in. Hopefully tomorrow and the next days I'll be able to gather more lectures. So the current topic is random variables. Sounds possibly a little difficult. I remember when I first was introduced to it, I did not understand what random variables were at all. But I hope that the explanations I will give you today will make it rather simple. So what happens is we might be dealing with a sample space, but that sample space is not immediately directly related to our interest. So for example, suppose that we are playing a Russian roulette, and the player of a Russian roulette, well, you know, the pistol supposedly has 7 chambers. You put a bullet in one chamber, you roll the chamber, and then you fire. So the participant of such a game is not so interested about the particular chamber that is in line of firing. What's more interesting is whether or not that chamber contains a bullet, whether or not the participant will leave another round. So how would that work? Here is the sample space we deal with. Those are the chambers. We can suppose that the bullet is placed in chamber number 1, right? And then which of those chambers will be selected? Since there are 7 and you presume the drum was rolled, you presume it's equally likely to be any one of those chambers. And therefore the probability it's chamber 1 is 1 over 7. The probability it's chamber 2 is 1 over 7, 3 is 1 over 7, and so on. All of them are 1 over 7. But what is the sample space of interest? It's much smaller. Either the bullet is in the chamber or the bullet is not in the chamber. So a random variable, in this case, is just a function from the sample space S that we are given to another sample space, possibly smaller, of outcomes that are of direct interest to us. So what is a star? It's just a sample space containing bullet or not bullet. So here is x, it's a function from S to S star, and this function will collapse the individual nodes or individual outcomes of sample space S to individual nodes or individual outcomes of S star. And what else? The probabilities for those individual outcomes in S star are directly related to the original probabilities in S. So for example, B gets only one thread, right? Only one fiber comes from 1 into B. From no other number do we see a fiber coming in. So the probability that B happens is the same as the probability that S equaled 1. And that is 1 over 7. And the probability that N happens is the sum of the probability weights on each of the fibers. So there are 6 fibers converging onto N. It's as if you took those equally weighted pebbles, pebble 2, pebble 3, pebble 4, 5, 6, 7, and you collapsed it into one heavy pebble, which has the sum of masses is the mass of that new pebble. Okay? So probability of N is 6 out of 7. The general situation is just as simple. So if I take a function x from a sample space S onto some set S star, so we would say that this function is called a random variable if it satisfies the following property. So if for any b belonging to S star, for any node in S star, I can calculate the probability of that point by taking the pre-image of that point under X and finding the probability. So this just means finding the thread or the fiber that is terminating at B and seeing where it goes, and then I calculate its probability. So here is what this definition means. So suppose that I have my original space is S, and it contains possible outcomes A, B, C, and D. And then we want to create a set S star by, well, in this case, identifying A with the number 1, B and C with the number 2, and D with the number 3. Now, A used to have some probability P sub A of occurring, B has a probability P sub B, C has probability P sub C, and D has its own probability. Now, how would I figure out what's the probability of 1? Very simply, I want to know what's probability 1, I just take the pre-image of 1. Which points then are mapped by the function x, the function that carries D to 3, C and B to 2, A to 1. Which of those points are mapped to 1? Well, I look, the inverse image is just A, so I just calculate the probability of A, which is P sub A. What is the probability of 2? Similarly, I look at 2, I take the pre-image. So the pre-image is just which particular values does x map to 2. You see, x equal to 2 is another way of writing the pre-image of 2. Which particular values are mapped to 2? Well, here is 2. I see that B and C are mapped to 2. So the probability that x equals to 2 is the probability of the event B union C, which, because B and C are disjoint outcomes, equals to the sum of the probabilities, P of B plus P of C. And that's how we get it. Similarly, what is P of 3? P of 3, I just take the pre-image, I see it's the probability of D. Now, do you see that this set S star has now been made an induced sample space? In other words, here used to be a set, and because the outcomes in that set are directly related to the original outcomes in the sample space that could occur with some probability, we see that the sum of the sum of the probability of outcomes 1, 2, or 3, in other words, the probability that some outcome in S star will happen, is the probability of P1 plus the probability of 2 plus the probability of 3, which is, you see, because those probabilities were identified here, right? So probability of 1 is that of A. The probability of 2 is the sum of B and C. And the probability of 3 is that last probability. Because those are the probabilities making the original sample space, they add up to 1. You see what happens here? The analogy is that the probability is like the weight of the stone. So those are pebbles or stones, and the probability is their weight. So what happens? You see that in this case, I just simply transfer the pebble. I just relabel it. In this case, I take two pebbles and I merge them together. I fuse them, melt it together to create another pebble, which I now label as 2. Now the combined mass of the new pebble is that of the pebbles that were collapsed together. And here again, I just simply transferred it. See, so that's how it works. There is a very strong analogy with quotient spaces, if you remember, right? So you take points. That's if you study the topology, you take points, you collapse them together. Of course, then there is discussions of continuity, but you have to have a surjective or onto function. Okay, very simple. Random variable is just a function from one set onto another set. The first set had to be a sample space, and what this function is doing is just collapsing the pebbles together, and then let's say the occurrence of the collapsed pebbles of the conglomerate pebble, it's the sum of the probabilities of the pebbles that made it, the sum of the weights of the pebbles that made it. Consider now this example. We have to select 3 randomly selected balls from an urn containing 20 balls numbered 1 through 20. We bet that at least one of those balls has a denomination of 17 or larger. So what is our probability of winning the bet? So the sample space we're given is the sample space of subsets of size 3 out of 20. And so how many nodes do we have? How many pebbles do we put in our space S? There are clearly 20, choose 3 different pebbles, and the weight of each is 1 over this number. But the sample space we might be more interested in is what is the largest denomination I got on my ball out of the sample 3. So it could be 3 or 4 or 5 all the way to 20. So what I do is I have a function that will map each pebble in here based on the largest number I found in the subset. So if the largest number is 3, then that will be mapped in here. How many outcomes are mapped to the number 3? Well, clearly only one. If the largest number is 3, and then I had to have the balls selected were 1, 2, and 3. So there is only one possibility. If the largest number is 4, I could have selected 4, 3, 2, or 1, 2, 4, right? So there are a few possibilities more. So you see that some events are carried over, and some pebbles in this case are crushed together into one outcome. So using this different sample space, we're going to calculate the desired probability. What do we want? We want probability that x is bigger than or equal to 17. And that is the same as probability that x is equal to 17, plus the probability x equals to 18, plus the probability it's 19, plus the probability it is 20. Yes? So what's the probability of 17? Well, think about it. 17th ball was the largest picked, so I have to make a sample of size 3. There are 16 possibilities for the 16 numbers smaller than 17. Out of them I need to choose 2. And all divided by 20 over 3, 20 choose 3. So similarly for 18, 18th is the largest number. So I have 17 possibilities for the other numbers. Out of them I select 2 and divide by a total of 20 divided by 3. And so on, right? For 19, it's going to be 19th ball is present, so I have 18 choices. Out of them I need to pick 2. So it's 18 choose 2 divided by 20 choose 3 plus 19 choose 2 divided by 20 choose 3. That's when I pick ball number 20. And so the combined sum you can calculate is slightly over 0.5. So that's my probability of winning the bet. Now let's consider another example. So we have a fair die, and let's toss it until we see the number 6 coming up. So let's x denote the number of required tosses. So to get a 6, we might have 1 toss, or 2 tosses, or 3, or 4, or some number n, or possibly infinite number of tosses. In other words, we toss and toss and toss, and never ever see the number 6. So our sample space might be the outcomes 1, 2, 3, 4, all the way to infinity. Let's consider what's the probability that we have 1 toss. 1 toss is required. Well, we have 6-sided die, it's fair. There is no preference which number should come up with each toss. So clearly that should be 1 over 6. Now, what's the probability that we require 2 tosses? Well, that means that I first must not get 6, and on the second trial I do get 6. So what's the probability of not getting a 6 on the first trial? clearly that's 5 out of 6, right? I can only get 6 one way, and there are 5 ways I cannot get 6. 5 ways I can fail. Now, independently of what happens on the first toss, the second trial will just do whatever it likes, so the probability of getting a success or a 6 on the second trial now is 1 out of 6 as before. So together we get 5 over 6 squared. Now you can consider what should happen at a general number n, right? So suppose I need to toss it n times to get a 6. That means that the first n minus 1 trials were failures. So each of them independently is a failure with probability 5 over 6. So first toss I will fail with probability 5 over 6, second toss I will fail with probability 5 over 6 and onwards, and I have to succeed on the nth trial. So they're going to be 5 over 6 to the power of n minus 1 multiplied by 1 over 6. And then let's observe what's the probability that I will require finitely many tosses to get to 6. So probability that x is an integer is the probability that x equals to 1 or 2 or 3 or 4 and so on and so forth. That's the probability here. It's 5 over 6 to the n minus 1 times 1 over n for an arbitrary nth number. And what we get is a geometric series. Observe that this geometric series adds up to the number 1. In other words, with probability 1, I will get a finitely many tosses. After finitely many tosses, I see that, I get a 6 and the game stops. With probability 1, the game will stop. And with probability 0, the game will not stop. That's pretty interesting, guys, right? If the probability that the game does not stop is 0, does it mean the game will not stop? Remember we talked about that before. So probability does not imply that it's impossibility. If the probability is 0, it does not mean the outcome is impossible. It just means it's unbelievable, right? If you toss and toss and toss and toss, of course, I mean, you might think, well, nobody can toss a die forever. It's physically impossible and you can completely dismiss it and the discussion is mute. But if you can imagine tossing it and tossing it and tossing it, maybe it's a punishment in hell, right? Maybe it's a Sisyphean effort. Maybe you roll the stone and it rolls back, and you roll it and it continues for eternity. What's the probability you roll the dice and this game continues to eternity? Well, 0 we say. But it doesn't mean it cannot happen. But what it means, that's why it's so difficult to understand it, right, is that if you actually somehow could witness that infinity, somehow witness this happening, you would not believe that the die was fair. You would not believe that it was random. Okay, so it's like a miracle, and the interesting thing about miracles is that you never ever believe in them, even if they happen. You never believe they are miracles. You would think there must be some other situation, some other possibility. And with probability 1, you are correct. Now let's specialize into discrete random variables. So a discrete random variable is one that either takes finitely many values or at most countably many values. So if you have not studied basics of Cantor's theory of infinites, there are going to be different types of infinities. And the smallest infinity is called countable infinity. I will not talk about this. You can watch, if you're interested, my analysis lectures about infinity, or you can look at a very short, very neat 8-minute video that I will attach below the comment section. So there are discrete random variables considered, and there will also be continuous random variables considered, and there can be some sort of mixture, right? So continuous but not everywhere. So what it means to be discrete is that the values where the probability isn't equal to 0, those values can be labeled as 1, 2, 3, 4, 5, and so on. That means you can count those values. So let's say x1, x2, x3, it could be that there are infinitely many values, but you can pair them with the integers, 1, 2, 3, 4, and onwards. Now, because we are dealing with sample space, and a sample space must have probabilities add up to 1, we see that probability of the sample space is then the summation from n equal 1 to infinity of p of xn, and we know that we must get the number 1. Here is a very, very simple example of a discrete random variable taking only the finite numbers 0, 1, and 2. So x is not 0 with probability, x is not, does not have 0 probability only at outcome 0, 1, and 2, where those outcomes count how many times did we get heads when we flipped a fair coin, twice. So if I flip the coin twice and get 0 heads, that's the probability that I got tail and tail. And that's 1/2 times 1/2 or 1/4. Now, the probability that I get 1 head means that it is tail heads that I got. So first throw of the coin landed on tails, second on heads, or first on heads, second on tails. So each of them has probability 1/4. So 1/4 plus 1/4 is 1/2. And the probability of 2 is going to be the probability that I received heads on my first toss of the coin and on the second toss of the coin. So that's probability equal to 1/4. And here you can see it in the diagram. So you can adjust the diagram if you wish, right? In general, we would have those diagrams, those rectangles, the probability should be represented by the area, but not in the picture I produced. So what you have is the probability of 0 is 1/4, the probability of 1 is most likely, it's 1/2, probability of 2 is 1/4. So this 1/4 plus 1/2 plus 1/4 adds up to 1. If x is a discrete random variable that takes the values x1, x2, x3 onwards, those countable values are the only ones that x can take with non-zero probability. We will say that the probability creates a function on those nodes, and we call that function the probability mass function. And why do we call it this way? Because it feels like if I think of x1, x2, x3, and so on, if I think of them as pebbles, the function p assigns weight to those pebbles. So let's consider how that works. So suppose that we have a function x, a random variable x, that corresponds to a probability mass function that is defined at each integer, at each positive integer n, well, 0 and onwards. So the weight of the integer n is some constant multiplied by lambda to the n divided by n factorial, where lambda is some positive value. This is a bit abstract. We will have this example will recur with the numbers later on, but bear with me. We want to figure out what is the probability that x equal to 0, and also what's the probability x might be bigger than 2. So the first thing we want to do is this c, we can figure out what it must equal to. What is that c? Well, first I know that if I am given a probability mass function, then the summation must equal to 1. But what is that summation? That's the summation c sum n equals 0 to infinity of lambda to the n over n factorial. You surely recognize this sum as e to the lambda. That's nothing more than e to the lambda. And what do we get? We get that C equals to e to the minus lambda. Now we can try to solve problem A. We're asking what's the weight of pebble 0? Well, that's very simple. The weight of pebble 0 is simply, according to this formula, is C, which is we now know to be e to the minus lambda, multiplied by lambda to the n over n factorial. Well, but what is lambda to the n? In this case, n is 0. So it's 0, lambda to the 0 over 0 factorial. What's lambda to the 0? Well, that is 1, and 0 factorial is defined to be 1, so we get e to the minus lambda. What about B? How do we solve that? Well, it's more convenient perhaps to write this probability as 1 minus the probability that x is less than or equal to 2. And what is this number? Well, nothing more than 1 minus the probability that x equals 0 plus the probability that x equal 1 plus the probability that x equal to 2. So that simply is 1 minus e to the minus lambda plus e to the minus lambda times lambda plus e to the minus lambda times lambda squared over 2. So if we knew lambda, we could make it a definite value. There is still one more concept that I will just gloss over: cumulative distributions. So they become very important once we get to continuous random variables, but let's just for now quickly say what it means for discrete random variables. So if I have a discrete random variable x, and I pick, and this random variable is real value, it produces only real numbers, and I pick a belonging to R, so we might be interested in the probability that x is less than or equal to a. And this function, capital Fx of a, would figure out the probability that x is less than or equal to a, is a function known as cumulative distribution. So how do you evaluate it? Well, you get a, and you just sum up all the probabilities for each xk that has a non-zero probability that is less than or equal to a. So a quick example here is how it might work. So suppose that x has the probability mass function that at 1 it's 1/4, then at 2 it's 1/2, at 3 it's 1/8, at 4 it's 1/8. So what sort of function do we have? Well, we see a piecewise function defined as follows. If I select a number a smaller than 1, well, no value smaller than 1 has non-zero probability, so probability is 0. So anything below 1, the probability is simply 0. What about the probability that a is between 1 and, well, if a is bigger than 1 and less than 2? What's the cumulative distribution at a? That means I'm asking for probabilities below this a. Well, if a equals to exactly 1, I just add 1/4. Now for any a that is between 1 and 2, the only non-zero pebble I've gathered, I always gather pebbles from the left, the only non-zero pebble I've gathered is 1. So the probability stays to be 1/4. You see? And then all the way until I'm about to reach 2. As I go across 2, look what happens. 2 or more, now suddenly the probability is what? The probability of 1 is below 2, and 2 is equal to 2. So the probability now is 1/4 plus 1/2. 1/4 plus 1/2, which is 3/4. So we are here. Now, until I reach 3, nothing else is gathered. So probability stays the same, right? If I ask what's the cumulative distribution for any value a between 2 and 3, well, below this value, I only gathered the pebble 1 and the pebble 2. So my combined mass is always the same. It's always 3/4. Because you see, those pebbles between 2 and 3 are not giving me any new mass. They are 0 mass pebbles. So then, until I reach 3. Now what's the cumulative distribution for a bigger than 3 but less than 4? Well, it's all the pebbles scattered on the serial number line, but most of them weigh 0. So the only ones that contribute mass is 1, pebble 2, and pebble 3. And we sum up their masses or their probabilities. That's 1/4 plus 1/2 plus 1/8. And we get 7/8. It always stays to be 7/8. I haven't gathered anything. So you see, when you see a jump in this cumulative distribution, means I picked up another pebble that actually weighs something. And then once I get to 4 or onwards, I've gathered all the pebbles that weigh anything, and my total weight is 1. So I hope that is pretty clear.